Hello. So last lecture we learned about the viscosity. The thing is, and we learned that after achieving the steady state, velocity will be a function of only z. It will be a function of only z. So now we want to calculate the force, meaning what will be the force, viscous force, which is similar to the friction. It's a different name. So when we say velocity will be a function of z, I mean to say if you go for any value of z here, let's say I'm going z here. So this velocity we can write as a function of z, only z. So as you go up, as you keep changing the value of z, the velocity will keep changing. So now what we are doing, we are making the velocity profile here. What does that mean by velocity profile? What I mean by velocity profile is I go for z and it will be having some numerical value of z, and that numerical value of velocity I will represent by a vector. So this vector, the direction of this vector represents the direction of velocity of the particle, and the length of the vector represents Vz, magnitude of Vz. So you see, as we go up, the magnitude will keep changing, so the length of the arrows keeps changing. Okay. So here I have taken one example of it actually. So when you have this velocity profile, you will have the velocities, and if you join the tip of the vector, these tip of the vector, sometime you might get the straight line, different straight line you might get. And sometime you might get a function, parabolic function also. If this is more, you will get the parabolic function also, or you might get some different type of function. You might get some hypothetical function like that also. So everything is possible. It will depend upon the liquid and the surface, real case scenarios, different things you will get. So one more time, we are going for z, and the velocity as a function of z, we are representing by an arrow. And as we learn in vector, for a vector, the magnitude of the vector is represented by the length of the vector, and the direction is represented by the direction of vector. So this arrow represents the velocity. So this arrow might have different length. And when we join the tip of the arrows, we will be having a curve. That curve, by joining the tip of curve, this curve is known as velocity profile. This curve. And this curve might be a straight line, this curve might be a parabola, this curve might be some different function by joining the velocities. It will be case to case basis. Okay, we might have different values, and we'll go till the topmost point. Okay. So this velocity, and these particles will be experiencing some of the friction, which is in backward direction as well as forward direction. As we know, the friction, there will be two friction acting onto the particle, one in backward and one in forward. And both of the friction after achieving the steady state is same. And if they are same, if either I calculate this friction or I calculate this friction, I know the friction. And this friction reaches till the topmost point. So if I calculate the friction at this point or this point, both are going to have the same value, because after achieving the steady state, every friction becomes same magnitude wise. So you see, that's the thing. And now we want to calculate that friction force. In this chapter, we call it viscous force, and we represent by Fv. So we want to calculate that Fb in this source. Okay. So when empirically we calculate the Fv, the value of Fb, empirically when we calculate that, the value of Fb comes out to be proportional to cross-section area A. What cross-section area? It is a cross-section area of the layer you are studying. So basically, we are deriving this thing for a particle, but actually we are not going to see the particle. We are going to look at the layers, and layer will be having multiple particles. So these layers will be having some cross-section area. Then bigger the cross-section area, bigger the friction will be there. Smaller the cross-section area, smaller will be the value for force. Because you see, viscous force is acting onto the particle. If you are going for bigger area, number of particles will be more. And if you are going for a smaller area, number of particles will be less. So viscous force will be proportional to cross-section area of the layer. It is of layer. Okay. And when you further calculate that, Fb comes out to be proportional to dv upon dz. This is the velocity gradient. Not the rate, but gradient. Meaning rate of change of velocity as a function of z. It comes out to proportional to Fb only after achieving the steady state, not before that. So after achieving the steady state, the viscous force comes out to proportional to dv upon dz. So as how the velocity is changing as a function of z, it is proportional to that. Okay. So if we combine these two things, this is velocity gradient. If we combine these two things, upon combining, If we combine these two things, then FB comes out to be proportional to A dV upon dz. There is a proportionality constant, there is a proportionality term, we have to introduce some constant for it. So if we replace this proportional sign by a constant, that constant is defined as eta. Eta A dV upon dz. This is called as eta. It's a constant, but not the universal constant, it is a local constant. Basically, this value depends upon what kind of liquid you are using there. So the formula becomes, viscous force becomes eta A dV by dz. And you see, this whole function will be independent of time, because if it is not independent of time, it's not a steady state. So it has to be steady state. This value, when you calculate this value might comes out to be constant, this value might comes out to be as a function of z depending upon the different velocity profile ultimately. This dV by dz we calculate for these. So it might be a constant for this kind of function, this kind of profile, it might be a variable for this kind of function, and it might be a further variable for this kind of profile. So this becomes your viscous force, the value of viscous force only after achieving the steady state, after achieving steady state. The same viscous force will be acting at the bottommost point as well as the topmost point. This eta is defined as coefficient of viscosity. And the thing is, if you want to call it viscosity constant, it's well and good. There's no problem in that. It is that constant which is similar to the mu, basically. Coefficient of viscosity, its unit, when we define the unit for eta, its CI unit is poise. Poise is a CI unit. And generally, if you know, we don't use the CI units. When we use CJ unit, we don't use. CJ unit, we don't use. When we use that thing, we use the units into the questions, generally we go for the SI unit. So when we convert this unit into the SI unit, meaning unit for eta, in SI, when we convert that, it comes out to be 10 poise. So if you are using whatever value you are using, if the value is given in terms of poise for eta, you multiply it by 10, and that value you will take for the SI calculations. Okay? So that's how you calculate the viscous force. This is a formula. So to calculate the viscous force, you need the cross-section area of the layer on which you are calculating things. You need the value of eta. That value of eta will be provided to you in terms of poise, which you have to convert in terms of SI unit, which is 10 times of poise. Okay, and then you will calculate the dV by dz. This dV by dz might be constant, it might be variable. Generally, when we go for the IT exams and the CBSE exams or any exam, engineering exams or even medical, this value comes out to be constant. So generally, an examiner concentrate on this type of velocity profile. Okay, so when you calculate dV by dz, you get the FB, and that FB is similar to the friction force. Okay, so in case of dynamics, it was very easy to calculate friction force. It was mu times of n. But here, you have to calculate area and dV by dz. It becomes a little bit tricky, but ultimately, you have to calculate that. Okay, so now I will do some problems there. Thank you.